without further ado, by the way, I thought this was a great picture, Joe. Joe picks our images.
Yeah.
And in an Art Deco theme, um, following our sort of design aesthetic. He gave an alternate one for fun. This kind of reminds me that our C3PO it does sort of look a little bit Art Deco. But anyway, so oops, we have a typo here. But Yaqi, we've been working with for a while, and you can leave this up, but go to our website, find out more. She's just coming out of CMU, the Robotics Institute, and on the job market. So take a good look. She's one of these promising wave of next stars. So please take a look. And um, now comments. These are the different ways to ask questions: Discord, YouTube, or LinkedIn. Okay, and we've been getting them from all of them lately, so any of them is fine. And we'll put up Yaqi's information or send this out if desired on Discord afterwards, so you can find out how to contact her. Okay, and just quick preview for next time. Next week is a great title, by the way. Sridhar will be next. All right, with that, take it away, Yaqi.
Great. Thanks, Alex, for the warm introduction. Hi, everyone. I'm Yaqi. I'm a postdoc at CMU and got my PhD from National University of Singapore. So today, I'm very excited to share my work on knowledge-guided AI partner. So what is AI partner? AI partners are intelligent agents that can understand us, communicate with us, and assist us in many different tasks, like in our homes or in the factory, like can assemble, disassemble, maintain, or repair. And we have been waiting for this for a long time. Until recently, we see this. So this is a demo video from Robot Neo that come from, I think, last year. It shows a home service robot that can do all kinds of household tasks. It can boil some water, do the laundry, and clean up the floor. Also, this robot from Tesla, who can serve popcorn to humans in their newly opened restaurant in LA. So it seems that they are here, like all those ideas in sci-fi becomes true. However, it's not that easy. So these two demos I just shown, they are human teleoperated, which means there is somebody in the office actually controlling the robot. And it sounds a bit creepy and also poses severe privacy issues. And there are also many other cool videos that you can see online, but they are task specific. They do not generalize well, and they are so brittle. If you change some part of the environment or even change the position of the object, they might not work. So why is the case? Why is it so difficult? This because we only have limited data in embodied data, so which accounts for the actual grounding, physics, and all kinds of like interaction and action with the physical world. Like if you compare the state-of-art robotics data, the OXE and Pi0 with language data, you'll see they are way, way, way fewer. And this is a real challenge we are facing now. So this is a video from last week. This robot seems like walking to the audience, everything is normal, but suddenly loses its balance and fall down. And in many other scenarios, like one of the players decided to quit this soccer game. And this is a marathon game. And many other cases on the street, in the corner, and rolling down the hill, and also Tesla robot falling down. And you can see clearly from his gesture that it's a human panic gesture. It's a clear sign that it's teleoperated by human. Okay. There are also like some other scenarios in autonomous driving. So these two cars, they are Waymo cars. They get confused with each other, then start to do some weird things, go back and forth, and cause a traffic jam. Then the most obvious solution is that we can just get more data to fill in the data gap. We can throw a bunch of robots in a room to collect more data, basically. This is what we can do, and we can even be smarter. Like we can throw a bunch of robots in the room and let the robot itself decide what action what task to perform to collect more data. And this is the work done by Google. If you have enough money, you can make it work. And the other way is we can also collect data in simulation, which is less costly. But the thing is, if we want to collect in simulation, we need somebody to sit down to design all the scenarios. So it doesn't scale well because it's hard to cover all the long tail distributions and edge cases. There's also seem to real gap. So it seems that just like brute forcefully collect more data is not going to solve our problem. Why? Because the data gap is too large. If you compare the robotics data, the OXE and Pi0, with the language data, you can see that the robotic data is not even a pixel of the language data. The data gap is too large. Then how to do it? Does it mean that we cannot solve it at all? But wait, let's look at the human data. The human training data is 5 orders of magnitude fewer than the language data. But human generalize way better. Like these two persons, they are collaborating in making a salad. And they are like adapting to each other, collaborating with each other very smoothly without needing tons of samples. So what it gives? It's clearly that the performance is not just about how much data we have, but it's about how we use it and how we organize it in our mind and our internal representations. And in machine learning, we call this inductive biases. So in this talk, I'm going to talk about how can we develop similar inductive biases for the neural models to make them have to be more effective without needing more data. So here is some visualization. Suppose this is our hypothesis space. And originally, the model only learned from data. And the final solution, basically the learned model, could be anywhere in this space. And our inductive biases are essentially just adding constraints into this space. So you can clearly see that they can narrow the search space, make it easier to learn. So basically, this information we are encoding here are exactly the things that the model does not need to learn from data, but we are providing to the model upfront. Therefore, makes the learning much more effective. So in this talk, I'll mainly be discussing using symbolic knowledge as an inductive bias because I found it is particularly useful, and I will tell you why. There are also many other inductive biases, for example, consistency, which I will also cover in my talk. And particularly, I'll mainly cover 3 types of symbolic knowledge: the formal logic, like propositional logic or linear temporal logic, and knowledge graph and ontology. So the problem I want to solve is how to leverage the knowledge-guided inductive biases to improve the model and without needing more data. So this is what I want to do. Instead of just collecting more data to train a better model, I want to leverage knowledge-based symbolic knowledge to make a better model. So before we talk about how to do that, let's look at some examples of symbolic knowledge. So here is the example of knowledge graph, which related to the current observation. So we have the objects like the zucchini, the knife, the pillar, and the cutting board. we also they have their functions that the knife can cut and the cutting board can support. Then we also have their affordance, like for example, the zucchini is peelable and also cuttable. Then also other properties like the knife is sharp and the cutting board is flat. Then we also contains some common relations between the nodes. For example, peelable and can peel should be connected. And the knife cut on the cutting board is also a common relation. Next, let's look at the propositional logic. So the propositional logic contains the propositions. For example, the propositions could be like cuttable zucchini, which is true in our scenario because zucchini is indeed cuttable. And holding zucchini is also true because in the current observation, the human is indeed holding the zucchini and holding the knife. But holding the peeler is false in this particular scenario. Also have other propositions like the zucchini is on the cutting board. Then if we want to express the knowledge that if you want to cut the zucchini, then you need to hold the knife and the zucchini must be on the cutting board and the zucchini must be cuttable. You can express it as this. So you can define the logic relation by using this kind of formula. For example, cut something implies holding knife, and that object is cuttable and that object is on the cutting board. But however, this propositional logic can only capture static rules. How about we want to capture some ordering rules, which involve some temporal relation? Then we will need a temporal logic. So in temporal logic, we have additional temporal operators. Like for example, next, eventually, until, and wait until. The difference between until and wait until is that in until, the second clause must be eventually true, but there's no such requirement in wait until. And suppose we want to encode the ordering rule that you need to wash something before you cut it. Then we can write down something like this. So we do not cut that objects before we wash it. And we can also use until to represent the wait until, because the wait until is a derived operator and all others are basic temporal operators. So we can use the basic temporal operators to represent all others. Then one could be something like this. We can add additional clause saying that we globally do not cut that object at all. So in this talk, I'm going to talk about, firstly, how can we integrate the symbolic knowledge into the neural models? Then how to leverage it to have a better understanding of the world. How can we have more robust and reliable perception? And finally, how to use it to collaborate with humans better to make a trustworthy decision and collaborate with humans actively. Now let's look at the first part. Suppose you gave this image to the model. We have the person and the slide, which we are interested in. And as a model, the traditional vision model, what's the relation between the person and the slide? The model may tell you that the person is eating the slide. And as a human, you know it's not. Is that the person is pretending to eat the slide, but actually it's not, because the slide is not edible. We know we have this domain knowledge so that we can make such decision. Can we actually input this domain knowledge into the model and make the models predict only feasible solutions? Yes. So we can just write down this formula and I simplify a little bit. So our first option is that we can just embed it, right? Embed it into a neural representation. So we can embed it just as it is, as a string, like how we embed a sentence. But the problem is the clause ordering is irrelevant in a logic formula. But if we change the order of the word in a sentence, for example, the semantics will change. But if we change the ordering of the clauses, the semantics of the logic formula will not change. So this probably is not a good idea to embed as a string. So our second option is that we can convert it into a graph. So this is a syntax graph. we have the general form, also have the standard form, the CNF, the conjunctional clauses. So our second option is we just embed it as a CNF logic graph. But here the problem is a single semantics in CNF could be written in infinite many forms. This is because the CNF only encodes the syntax. It does not carry any of the semantic structure. It encodes basically nothing other than the truth condition. But we do have a better option, the DDNF. DDNF is a DAG which contains only literals and the intermediate nodes are and or all. And it has two additional constraints. Deterministic, which means the children of the all node should be mutually inconsistent, which means only one of them can be true. And decomposable, which means the children of the n node do not share a variable, so they are expressed on different set of variables. So as mentioned, the CNF encodes only the syntax, and the DDNF is able to encode the semantic invariance by imposing these two constraints. So in this way, the DDNF explicitly encodes the factorization and partitioning, and it powers algorithms and have polynomial type model counting. Then our option 3 will be embed the DDNF graph and leverage the semantic information in this graph. Let's see how we can do this. We have the input formula, then we pass it through our graph neural network, which is our logic formula embedder. Then we do message passing among the nodes and pass it to the next layer and iterate over a few layers. Then we suppose this is the embedding, which is a neural vector in the embedding space of our formula. And those are the embeddings of the satisfying assignment and unsatisfying assignment initially. Then our training objective is we want the satisfying assignment and formula to be closer, and unsatisfying assignment and formula to be further away. In this way, after we train it, the learned embedding space, the distance between the formula and the assignment will be an indication of satisfiability. Then we can further use it as a regularization when we train our target neural network. And let's take a closer look at our logic embedder. It's based on graph neural network, but we make two additional augmentations. The first one is heterogeneous embedder, which means that we only allow the node with the same type share weights. And second is semantic regularization, which I leverage the two constraints in the DDNF and into the graph embedding structure to make it easier to embed the semantic information in the DDNF. As we mentioned, the children of all nodes should be mutually inconsistent, so I regularize them to sum up to 1. And the children of n node should not share a variable, so I regularize them to be orthogonal. Okay. Let's see how we can do this in practice. I suppose we have the image we mentioned just now. Then we pass it to a classifier, which is our target neural network. If you have an initial prediction, say the person is eating the flight, then what we are doing additionally is we are embedding our knowledge and the initial representation, the initial prediction into the same embedding space. Then we can measure the distance, as we just said. The distance in the embedding space is an indication of satisfiability and can guide the learning of the target network. Then we combine it with the prediction loss, then backpropagate the loss into our target model. So during testing, we'll only need the target neural network and we are able to correct its prediction. Next, I'm going to show our results on the real-world relation prediction dataset. And our model is very data efficient. The model only needs to train on 5,000 images. If you have ever worked with vision dataset, you'll know this is really tiny. So this is the performance of the baseline model without knowledge and with a binary logic checker. And our option 1 and option 2 and our option 3 embedding DDNF. And our final one is our method embedding DDNF with 2 augmentations. We can clearly see that our method embedding DDNF with 2 augmentations has the best performance by a large margin. Now let's look at the embedding space itself to see whether it's really consistent with our hypothesis. So this figure, the x-axis is a distance, and y is a percentage of satisfiability. We can see that in DDNF embedding, there's a stronger correlation between the distance and the satisfiability. And this is convergence. We can see DDNF with the 2 regularizations make it converge faster. We also establish a theoretical connection between the compiled forms and the ease of learning. So we quantify the embeddable demanding using the formula sets and show that the DDNF is strictly easier to embed than CNF. This is also the first work to embed formal logic as a graph to improve the target model's performance. And it spurred a new line of work like using a graph neural network to embed logic into a neural representations. Now let's look at how to extend to temporal rules. How can we encode the rules such as orderings? For example, we want to encode the knowledge that we need to cook the salmon before we serve it. Then our formula will be something like this. And in this work, I'll focus on linear temporal logic that interpreted in finite traces. Then we can just embed this as a string again, but we have the same problems as a CNF because the same semantics could be expressed in many different ways. Then our solution is we convert the linear temporal logic into a DFA because the linear temporal logic, the LTL, only contains the temporal specification, but the DFA is the operational semantics. So in this DFA, each of the nodes is a state that the current trace is in, and the edge encodes a condition that transits from the source node to the target node, which is a propositional logic. And because now we have logic on the edge, so our logic embedder is a hierarchical logic embedder. So we have edge embedder, which embeds the propositional logic on the edge. Then we have a meta embedder, which embeds the whole graph. Then we embed them into an embedding space. And similarly, we want the distance between the formula and satisfying assignment to be closer and unsatisfied assignment to be further away. So suppose this is our initial prediction. Then we can embed it into our embedding space and compare the distance between the embeddings of our formula and the embedding of the initial prediction, and use this distance as a logic loss to guide the training of the target neural network. So let's look at the embedding space. The figure on the left shows the embedding space of a linear temporal logic syntax tree. And the graph on the right shows the DFA, the embedding space for a DFA. We can clearly see that the embedding space of the DFA is clearly separable, but it's not the case in LTL syntax. Here is some performance. Compared to a binary logic checker, our model is able to have a better performance on both actions and ingredients predictions. And this is an imitation learning task. The task is to design a recipe from a random set of ingredients. The knowledge we are giving here is a dependency graph of different status of the ingredients. And we can see that our model is able to make the algorithm converge faster. So far, I have talked about how can we integrate some symbolic knowledge into the neural models. So the key takeaway here is that the knowledge essentially acts as an inductive bias to narrow the search space. Therefore, we can improve the learning efficiency. And just as I mentioned, different types of knowledge have different strengths. For example, the temporal logic is able to capture the temporal relations. Also, the representation of the knowledge also matters, like the CNF and DDNF. So next, let's see how we can use it to understand the world. So now let's consider something pivotal to the embodied agents, the perception. Suppose we have the autonomous driving car here, and this could be something it's seeing, but it's not that always that clean. It could also be something like this. We have the pedestrians, the kid playing with the ball, and also sun glare, and also one of the objects is occluded by the sun glare. There also could be other conditions like snow, rain, smoke, fog, and whatever. So a reliable perception is very challenging. Then how can we leverage the learned knowledge representation to improve our perception? By taking the example just now, so as a human, I can still see like some part of the tail of the object that occluded by the sun glare, or some of our nose and legs also is furry. So as a human, I can tell that it's some kind of like furry animal, and because it's close to the human, it's probably pets. And because its nose is probably a dog. So I can make this hierarchical inference because I have the hierarchical knowledge. So can we put this hierarchical knowledge, which is ontology, a combination with ontology and the knowledge graph, into models? So the information will look something like this. We have dynamic objects. We have the human, animal, and vehicle. And human can further be classified into the adults, child, and pet, dog and cat, and many others. Then we have fixed entities as well. Then we also denote the common relations, like the human is really accompanying a child, and pet is leashed to human. And both human and animal could play with the ball, and other spatial relations. So how can we integrate those graph knowledge, the ontology and the knowledge graph into our models? Is the first thing we use an object detector to detect the available objects in our current observation. For example, detect the adult, the bus, the car. Then we connect the nodes with the same type between our observation and our knowledge graph. Then we do graph propagation, and next, after we have the representation of all the nodes and the visual representations, we enforce the model to perform the hierarchical inference. Like for example, if we want to predict this relation that's occluded by sun glare, we ask it to predict its silver class first. Is it an animal or food or artifacts? Then after decide it's animal, we further ask whether it's a dog or cat. And we are doing this for both objects and relations. And this could be something we get finally. You can see that we are able to recover what's occluded by sun glare by leveraging some partial features and also its surrounding objects. And the other thing is there are so many types of corruptions, like some examples showing here, the sun glare, the severe weathers, and the smoke and whatever, or dust. So we cannot train all those different types of corruptions. And we want our model to be able to zero-shotly transfer to any type of corruptions. So in our approach, we do not need to gather more data in the corrupted scenarios. Our model only trains on clean images and zero-shot transfer to the corrupted observations. And we have sorted performance on both clean and corrupted settings. The other problem is there might be some uncommon scenarios. For example, if you ask the vision language model to describe the image, like how many handles does this mug have? It might tell you that the mug has one handle. Why? Because in most of the samples I've seen, the mug only have one handle. So it's biased by its data distribution. And it's so uncommon that the mug have two handles. So this is one of the major barriers because the model hallucinates because the training data is usually unbalanced. So our intuition is we ask the model to show its own work. And we generate another image using the initial response. The model says the mug has one handle, so we use it to generate a new image. Then the mug will have one handle. Then we compare the generated image and the original image. If they look the same, it means the initial response is perfect. If they look different, it means there might be some mistakes in the generation, and we want to correct for that. Let's see how we can correct for that. Suppose this is our original image, and the model says the mark has one handle, and this is the logit when it generates the token 1. You can see that the probability of generating 1 is slightly higher than the probability of generating 2. Then we use it to generate a new image and ask the model again. Then suppose this is the logit. When we ask it to generate again, when generating the token or 0 or 1 or 2, because the image shows indeed a mark with one handle, so in this case the probability of 1 will be really high. Then in this case, we measure the similarity between the initial logits and the generated logits, and we found that there are low similarity. So we do contrastive decoding, which means we subtract the first logit with the second. In this case, because the probability of 1 is subtracted with a really large number in the second logit, so the resulting logits, the probability of 1 is lower than the probability of 2. Then we replace the generation logits with our new logits, and we are able to correct the model's response. Then how about the initial response is accurate? So we ask the model, and the model correctly says that the mark has 2 handles. Then suppose this is logit, and we generate another image. And because in the new image, the mark indeed have 2 handles, so in the second pass, the logits will look very similar to the first one. In this case, we will do a collaborative decoding, which means we reinforce the prediction and sum them together. You can see that the margin between the token 2 and 1 is larger. In this way, we are able to maintain the correct prediction of the model. Now here are some quantitative examples. Like for example, in this very strange scenario, I would say, that the man is riding on the yellow car and wearing a blue shirt. But the model hallucinates that the man actually is sitting on a small folding chair, because the man riding on the car at the back of the car seems very uncommon, and our model is able to correct for those hallucinations. And our model is training-free and plug-and-play, and has solid performance on 6 benchmarks across 3 different large vision language models. So we have seen like how can we use it to have more robust and reliable perception to understand the world better. The key takeaway here is the data imbalance. It really poses challenges for the data-only models. So beyond just collecting more data brute forcefully, intuitive bias can actually introduce some structured expectation about the world to make the model more robust and trustworthy. And lastly, let's look at how can we use it to better collaborate with humans. So we have seen how to use learned knowledge representation to have better perception. Then how can we use knowledge representations to actually improve our action decision process, to actually collaborate with human better and be proactively infer human intention and actions. This is a demo from our work. So it shows that the human is making salad, and the robot is observing what human is doing in a very short window. Then it's going to anticipate what human is going to do. For example, currently, I think the human is cutting the lime. Then the robot anticipates the human wants to put the sliced lime into the salad bowl. Then it's going to help with that. And now the human is mixing the dressing, and the robot thinks they're probably missing salt. Then help to put some salt into the dressing cup. Then after the human stir the dressing, and the robot is able to help pour the dressing into the salad bowl. So the main challenge here is we only have really limited observation windows. Then how can we achieve a fast action anticipation, like proactively help humans with such a short observation? Our solution is we can leverage some context information in the form of knowledge graph. For example, this knowledge could be the tomato is washable, cuttable, and the knife can cut and it's sharp. So this kind of common sense knowledge. Now another problem is we also need to model how they interact with each other over time. Then our solution is to use a neuro-symbolic graph search. So the first step is from the current observation, like the cutting board, there's a lettuce and tomato and a knife on it. We use object detector to detect the available objects in our current observation. Then we connect the detected objects with the nodes in our knowledge graph. Now here we can see that the cutting board is not detected. Maybe there's some noise in our object detector or what. I'm going to show how it's going to be activated by our graph propagation. Then after we connect this, we propagate to the neighbors of the activated nodes. For example, cuttable, or can cut, or sharp, or washable, and also cutting boards. Then we use the importance network to decide whether the neighbor, the candidate, is indeed relevant to our current observation. We can see here that the cuttable is activated because there's a knife, there's a cutting board, it's indeed a support action cut. But the washable is not, because there's no sink to support action wash. And the cutting board, again, is able to be activated even if it's not initially detected. Then we iterate a few times until it covers this, and then it will be our final selection. Then the final selection will be used to improve our video encoder and action decoder. Like we are actually adding another module here to actually rebalance the video features in our video encoder and action decoder. So how we do this is we add a rectification matrix from our symbolic knowledge to actually rebalance the query and the key pairs. Now let's look at whether it really works. I see the attention distribution. So the figure on the left shows the attention distribution from the baseline model without knowledge. We can see that it's mainly focused on the current action with cutting the lettuce, and other distributions are pretty uniformly distributed and not really focusing on anything. But in our attention distribution with knowledge, we can correctly focus on the future actions objects, like the plate and the salad bowl. So it means using our contextual symbolic knowledge, we are able to make the model focus on the objects that are related to the future actions. Let's see the results. So this shows two settings. The first one is when we observe only 6 seconds of observation, and second is 12 seconds. And the blue bar shows the baseline model without knowledge, and the green bar is our model with knowledge. We can see our model performs better than the baseline model on both settings. And then if we compare the margin, you'll see that the margin is larger when we have shorter observation. So it means that the reasoning with data is especially useful when our observation is limited. And our model is also sample efficient. It only needs about 10 robot videos, and it can do fast action anticipation from only 6 seconds observations. Then to support a fine-grained collaboration, it also need to do some instruction-oriented grasping. For example, if you ask a robot to hand over the hammer, then the robot should grab the head of the hammer and leave the handle to the user. But if you ask it to pick up the hammer, then the robot can just pick up the handle of the hammer. At the same time, the robot should also consider the domain knowledge and also its own capabilities. For example, if you ask it to hand over the iron, it still should grasp the handle of the iron because the head could be hot and can potentially damage its gripper. So let's see how we can do this. Is that we gave it a structured guidance. Then we fill in the blanks using LLMs. In this way, we are able to achieve a zero-shot task-oriented grasping. Let's look at some details. Suppose we have sunglasses that we want to grasp. Then we'll firstly use convex decomposition to decompose into some basic shapes. For example, the circle or the rectangle. Then secondly, we ask LM to identify which part is what, and then fill in the other properties of that part. For example, the circle corresponds to length, and the rectangle corresponds to the arm, and the length is small and fragile, and the arm is sturdy. Then next, we pass the complete graph into the model to let the model decide which part to grasp. And we can see that the model is able to successfully pick the arm and pick out the sunglasses. And there are some more examples. When you ask the robot to hand over the mark, it will grasp the body and leave the handle to you. And if you ask it to pick up, it will grasp the handle of the mark. And this is an example of how it's able to consider its own capability. That if you tell it the width of its gripper, it's able to do the calculation and the reasoning. For example, compare the width of its gripper with the width of the object. So in different scenarios, it will decide whether to grab by the head, or by the neck, or by the body. So here are more examples. Like it's able to differentiate, open the saucepan, or pick up the saucepan. If it's pick up, it should pick up the handle. If it's open, it should pick up the lid. And when you pick up the flower, it successfully identified it should pick up from the stem, not the flower itself, because the flower itself is fragile. And also is able to differentiate, like picking up a tissue and picking up tissue box. So our model all perform like Graph GPT and GPT-4o. So far, we talk about how to collaborate with humans. So the key takeaways are human-robot interaction, especially if we want to do that proactively, and we only have a very limited observation. So knowledge actually provides a structural prior to enable a more efficient and adaptive collaboration in real time. So in summary, we had talked about how to leverage knowledge into the neural implementations, and how we can leverage to understand the world better, have more reliable and trustworthy perception. And lastly, how to collaborate with humans proactively in real time. But although they are reliable and generalizable, but they are still static. So after deployment, the model and the knowledge stay the same, they do not change. But a real AI partner should be adaptive and self-improving. In order to do that, one important step is we need to make the model be able to learn some new knowledge, because our predefined knowledge is always incomplete. We want the model to grow its knowledge base. So here is, for suppose there's our intelligent agent, and it has some new experience. This experience might be something new. Could be some complementary knowledge to its existing knowledge base, or could even be conflicting. Then the model need to identify what are the abstractions that are useful and update its knowledge base, and still maintain a global consistency. During this process, we can provide some structural guidance and also provide some prior when it organizes the knowledge. And the updated knowledge will again be used to collect more experience and data. So this is a continuous learning process. I have two ongoing works on knowledge induction. So the first one is linear temporal logic induction, which learns a linear temporal logic from a set of expert trajectories. So the idea here is we are using hierarchical search. So we break down the longer traces into the smaller ones, Then we discover the temporal roots for the smaller fragments. Then we compose them together again to find the final formula. And the second one is neural predicate invention from long horizon task planning. In this work, we are using consistency as a feedback to guide the model to self-identify the relevant abstractions, which are the predicates, from expert videos without any annotation. And then we show how we can use the discovered predicates to pass it to a bi-level planner to support long horizon task planning. And the second step is the agents also need to adapt to user-specific needs, because every user may have different preferences, habits, or risk tolerance, and many others. And the true planner need to adapt quickly, safely, and stably. We can learn from human interventions, feedbacks, or some implicit signals. But a data-driven adaptation might be opaque and inefficient and even overfit. So we can actually leverage our knowledge base, but we need to separate the knowledge layers into the global layer, which accounts for the general knowledge, and the user-specific layer, which is adaptive to individual users. And the third thing is explanation and trust calibration. The collaboration between human and AI is not optimal if the human do not understand the agent's action. And we have an advantage here because we have our knowledge structure, so we can use the same knowledge structure for both reasoning and explanation. Suppose, for example, we can use a minimal knowledge trace as explanation. In this way, the explanation is not just an ad hoc explanation, but rather something the model is really reasoning with. And its structure is not just ascendancy, and also prevents hallucination. So in this way, the agents will know when and how to justify its actions. The other thing is we also need to model humans' trust towards the robots dynamically. We want to prevent both overtrust and undertrust. I'm planning to leverage some of my early works, which models how the human trust change according to the robot capability and intention differently. Then how does the human trust transfer to different tasks, and according to the similarities between different tasks. In this way, we are able to calibrate human trust and make the human maintain the right amount of trust. And in this way, we can support a transparent and predictable collection. Then this naturally supports us to apply our models into high-stake applications. For example, medical robots, like surgery robots and assistive robots, like for example, assistive feeding or dressing, who can take care of the patients and the elderly. And also some virtual assistants, like the agents are able to take care of your email or help you book some flights. And also our AI coaches, can teach us tennis, and AI tutor who can teach us maths. So we can apply to all those different domains, both digitally and physically. So in this way, the AI partner will not be static. They will be adaptive, self-improving, and communicate in human terms. So in summary, I have talked about how to leverage knowledge and how to use it to understand the world and collaborate with humans proactively in real time. I have also shown that the models are sample efficient and have a stronger generalization. So in one line, we can leverage structural guidance to learn intelligence more intelligently to bring us closer to the Jackson's lifestyle. Last but not least, I want to thank all my collaborators, advisors, mentees, and all the funding institutions and funding agencies that support my work. With all that, thank you for attending my talk. I'm happy to take any questions.
Thank you so much, Yaqi. Great talk.
Thank you.
I like how it evolved. Excellent. Okay, so probably have a bunch of questions. Go ahead, Olga.
Yes, not a bunch yet, but there are a couple of questions.
Mhm.
First question is, how does the reasoner of the system decide to do the best action in a specific context? How is it structured? In other words, could you explain how the decision-making process is structured?
I see. Is this question regarding a specific work? Because our decision process is a bit different. For example, taking the like collaborative salad making example. So what we do is we're using the knowledge as a context, and what action to do. So is decided by the is learned by our training samples. So the model will learn, for example, what the sequences of the task and what are the possible potential tasks or actions from data. And our knowledge actually is add as some additional information to make it more sample efficient. And but in our, for example, predicate invention paper, the actions is decided by a planner. So after we have learned all the relevant abstractions, all the like predicates, then we can directly use a bi-level planner, for which we have a higher level, which is a high-level task planning, like move to certain place, pick up the toy, put it in the cabinet, or web table, something like this. Then the low-level planner gives us a detailed trajectory, like how to get there, how to pick up the detailed joint positions.
Thank you. Okay, the next question. Would this be able embed in Mujoka? I personally don't know what it is, but maybe it's something from
Oh yeah,
robotics.
yeah.
Okay.
Mitigation is a common simulator in robotics.
Okay,
Yeah,
okay.
yeah, definitely possible. For example, in the predicate invention paper, we are using Mijoco as a simulation. Yeah.
Okay. The next one is from LinkedIn. Great presentation, thanks. I was wondering if you could clarify how big the models you train are and what GPU resources you use to train.
Yeah. In all the paper I mentioned, they are really small. So some of the works leverage a pre-trained LM or VLM, but in most cases we do not need to train them. Or even if we need to train them, we only need to train a very small adapter, which to align the new representations. And the GPU resources, I think we are using about two to four A6000 is pretty efficient, I would say. Yeah, because there's also limited resources in the universities, right? So we do not have tons of computations like in companies. So most of the models we trained and the GPU using are very sample efficient and resource efficient.
Thank you. The next question is, do all the symbolic rules and scene graph need to be annotated? If this is true, this is quite time consuming. Any new ideas to automate the process?
Yeah, first of all, the symbolic rule and the scene graph, they are different. So maybe you want to make the knowledge graph, because knowledge graph are the general knowledge that we are given to the model, which is general among all the scenarios. But scene graph is specific to our current observation, right? So it's something that discovered by the model, predicted by the model automatically. So the knowledge graph is the knowledge, and the symbolic rule and knowledge in the first few works I just introduced, I assume they are given. So how we get them is, firstly, we can extract such knowledge, the relevant knowledge, from the external knowledge base. So there are some available, really large knowledge graph, for example, that encodes the common sense knowledge, like the WordNet. It encodes a lot of common sense knowledge, and for example, the affordance or the functions of the different objects. And the other method is that you can use heuristics to learn directly from the training set. You can extract such knowledge directly. And the third one is beyond assume it's given, we can actually learn those knowledge Actually, that's exactly what I'm proposing in my future work. We should let the model to actively discover knowledge and integrate in its knowledge base. But what I'm thinking is that we will need to give the model a global structure of how to organize that knowledge in advance. And during the discovery process, we also need to provide some structural guidance to make it to make the induction process more efficiently.
Okay, thank you. And then a comment probably from the same person. Thanks. Exactly because of the limit resources I asked. And the same person asks, where can they find a link to the paper? And I just can mention that we have all the information about the talk, including links to the papers, on our Discord channel. And maybe, Joe, you can post the link to Discord somewhere on LinkedIn so that people from LinkedIn can join our Discord and see all the information, including links to the papers.
Yeah, and just to add on, I think this talk is recorded. Like if you watch the talk, I have citations at the bottom of my slides. You can just search for the title. Everything is online.
Okay, and we can share your slides, right? Are you okay with this? If we share your slides on Discord? Okay, great. Thank you. Okay, the next question is from Discord. You mentioned learning on the fly. So suppose you have an action like picking up a plastic cup, but your gripper is too strong and squeezes the cup. Would it then need to rely on the visual classifier to see that the cup is deforming? Or is there a way it can detect this by other means? And how would it learn to predict this later, discovering and remembering material properties?
I see. Yeah. So, for example, what we are currently doing in our work is we do have such detections. So after every actions and when a new state comes in, we actually ground the visual representations into our new symbolic representations again. So, for example, if we want to pick up something but we failed, then our grounding layer will automatically know that it failed. Then we start replanning. Then we can, in this way, we are able to recover the failure. And we also like currently have ongoing projects, the safety related stuff and also failure recovery. But coming back to your question, like for example, when the gripper is too strong and makes the object deform, in this case, it will need to, in the training sample, it will need to know what is the concept of deformed. If it's never seen by the model, I think it will be very challenging. Yeah, but yeah, I think it will definitely be an interesting direction. Like when we interact with the physical world, we're dynamically learning new concepts. Yeah, but yeah, I think the zero shot transform, but it still will be very challenging.
Thank you. And I think we're done with questions. Just one comment, no question, but this work was phenomenal, great work. And there are some reactions. Yeah, so our audience does like your work. Thank you very much.
Yeah.
I have one question.
Sure.
So it looks, you mentioned these knowledge graphs that you use, and it looks like it's pretty important part of your approach. And I'm curious if these are manually created. So you did briefly mention this knowledge induction, but I'm curious how promising this works. So do you still need some manually created knowledge graph, and then you can add some knowledge via this knowledge induction, and maybe other standard databases for some domains? For example, for cooking, this is probably one domain, maybe there are some other domains. So I'm curious in general, how many of those databases exists, and how promising you think maybe your work or like state-of-the-art research in this area, like knowledge induction and generating some knowledge graphs automatically.
Yeah. Yeah, I think you're right. In most of the work I just covered, I assume the knowledge is given. So which means we need to extract from external knowledge base and be verified by a human expert. Yeah. In later on works, I talk about induction part, but in the induction part, I do think we are still not there yet. So currently what we can do is we can discover the relevant predicates for the particular task. If we want to discover for example, for a general knowledge base, it's still very challenging. And we also need to find out a good organization structure for the knowledge for it to evolve over time. And while assuming data is given, I think it's pretty reasonable because there are a lot of cumulative knowledge in humans. For example, in a medical domain, say, we have the knowledge accumulated from the doctors. We can directly leverage into the model without letting the model to learn purely from data. And for example, in medical domain, the data is so limited. We cannot just do brute force, and there's no way to collect more real world data because there are limited patients, and also it's not ethical to do that. Yeah, so I think there are a lot of such cases that we only have limited data, but there are other more information, like the domain knowledge, that we can leverage to improve the model efficiency and generalization.
Mm-hmm. Thank you very much. These are all questions at the moment from the audience. Alex, do you have anything at your end?
Yeah, just to follow up on this last thread. So, and you mentioned, Yaqi, that you think you need still, even with knowledge induction, you need some kind of global structure,
Yes,
skeleton, let's say, for the knowledge.
exactly.
What are you using? And you actually have different kinds of knowledge you're using in different works, but at least in some of them, what are you using as your kind of global skeleton?
Yeah, for that thing, I don't have a very concrete idea yet. So currently, in my knowledge induction works, they are task specific. Like according to the different tasks, we choose a different architecture, different knowledge representation, and also a different architecture of the structural guidance. But if we want to have a general knowledge base, then I think we need to learn from human cognitive science to learn how humans efficiently organize the knowledge and the internal representations in a way that is also be able to leverage the existing knowledge to learn new knowledge more efficiently. Yeah, I think it's still an open challenge.
Okay. Did you have in mind something like, an upper ontology of some kind? Like, Wikidata is one, has this
Yes.
kind of upper ontology, or Psych has a certain upper ontology. You mean something like that?
Yeah. So in some of my work, I think we did leverage some of the wiki data. And if we want to have a global one, I'm not sure that will be enough. I think because currently I'm seeing that most of the knowledge, existing knowledge, symbolic knowledge base works, I'm using graph based, and we have explicit, the graph, and edge, and nodes. But I don't know whether a very comprehensive and global representation is indeed that structure, because that structure seems to be a little bit limited. I think in the future, I'm thinking of actually, for example, we could have hierarchical space, in hyperbolic space, for example. I think that might be more efficient because we will have a more efficient hierarchical structure. It can expand exponentially.
Great. Yeah. So this,
Oh, sorry.
oh, sorry. Just this is something we're working on. So maybe we should chat about that. It's very a fundamental issue. And of course, Yaqi's work is touching on many fundamental issues. But this is, by the way, those interested in this Neuro-Symbolic Agentic protocol, this is one of the essential things we're hitting in that project. So Yaqi, maybe we should talk about that.
Yeah.
All right, sorry, go ahead, Olga. There's another one.
No, I personally have another one.
Yeah, go ahead.
Yes, you started with showing all these failures of different robots. And I was curious if you know if any of those companies use some logic in those, and if you think these kind of issues could be fixed with logic. So, for example, when robot just loses its balance, Like, do you think it's just some problem with training, or you think that logic can actually help there, or like some knowledge graph or something? To me, as a person like not dealing with robotics, it looks like it's undertrained or something, limited data. But I don't see how it can be improved with logic when a robot just loses balance. But I don't have any experience.
Yeah,
Like,
I
what's your
totally
opinion?
got your point. Yeah.
Yeah, so I'm curious about your opinion.
Sure. Yeah, I got your point. Yeah, it's not that intuitive. Like taking an example, what I'm currently doing. So it's currently I'm trying to have like bring some safety guarantees into robotics. For example, you have a robot like manipulating stuff, for example. Then you want to ensure some safety. The first thing is about collision, of course. You do not want the robot arm to touch a person or crash with the wall, for example. The second thing is contextual safety. For example, if the robot was manipulating a glass, if we push the glass out of the table, for example, the glass will break. This is one type of safety. And also there are more tricky examples. If you want to pick up a bag of chips, but the bag is open, then if the robot actually pick from the bottom, then chips will fall out. Yeah, those kind of contextual safety is also very like brittle, I would say. It's very subtle. It's hard to learn from purely from data. So what we are currently doing is we are leveraging a word model then together with the vision language action model to enforce the model to actively like reason about the action effects. Then we use some critical states. We're planning to train a safety boundary. Then we use probing to interpret the semantics of the safety boundary. Then we can manipulate that safety boundary to integrate some additional constraint, which is hard to learn from data, for example. Then after that, after we have a trained and manipulated safety boundary, then we can leverage the word model to ask the robot to basically imagine what's its action effects, then to predict whether it's within the safety boundary or not. If not, we are trying to steer towards the safety region. So in this way, we are putting some knowledge, like the constraint, to manipulate the safety boundary. So I think the same thing can happen to, for example, to the humanoid example, that the robot falling down. Then when we perform some action, it should actually detect whether it's within the safety boundary or not. Yeah, but it's still very challenging because if we only have a control system, everything's easy. We can just add a safety constraint. But in the neural policy, it's really hard to interpret the semantics in the latent space. So we are still trying to do that. If we can do that, I think that would be a good thing to ensure some safety and guarantees.
Okay, thank you
Ju-
very much. Alex, yeah.
On that, yeah, you're. I think I was smiling when I saw your intro showing all the impressive demos that we're seeing all over the place on robots doing science fiction type things, and
Yeah.
the reality is they're really not. It's all remote control. So I think many people don't know that.
Yeah, exactly. Yeah, many of the cool demos showed in the stage are human controlled. Yeah, that's pretty sad. Anyway.
It's sad. But what would you, from everything you've seen, what would you say is the best real example of autonomy in these, especially in this? I mean, they're the wheeled robots, really being a somewhat autonomous, delivering things. But what about this sort of really articulated robots? Maybe dogs, humanoids, whatever. What would you say is the best real example you've seen of autonomy, even if it's for a limited task?
I see. Yeah, I think in terms like humanoids and quadrupeds, most of the examples I've seen, they are very task specific, I would say. Yeah, I can. Actually, I did see like a lot of cool demos. They can do like fantastic tasks. And the learning base is autonomous, but the thing is it won't generalize. Like if you have ever worked with vision language action models, which they claim to be the robot GPT, for example, then if you try with it, if you change some of the prompt or change the position, change the lighting, it will just break. It's so brittle and so unstable. I think it's not there yet. But I do think that, for example, the autonomous driving part, I think is pretty good right now. Although there is some failure cases, but mostly I think it's pretty good. I have been riding with all those autonomous driving cars. I think it's really good. And also the small robots for delivery, as you mentioned, the Starship robots. They are also pretty good. I'm seeing them in many cases, and there are also some failure cases that the Starship robot stuck somewhere. But most cases, I think they are working good. I think we are getting there, but it's not there yet, definitely.
Yeah, and even the stuff that's kind of working, autonomously, as you mentioned, it came at massive cost.
Yeah.
To the
Yeah.
current approach.
Yeah.
And if you want to go one level fancier, even with the same systems, it would be even, I would think, even more greatly expanded cost. So, all right. Any other questions, comments? Otherwise,
Yes, we do have one more question, one more comment, but on this topic, I have one follow-up question. So, Yaqi, do you think you have enough knowledge, skills, and expertise to fix one of those robots, even if in limited domains? For example, I heard some feedback about these robotic pets, and the feedback was not very positive. But this is one example of a robot in limited domain. So do you think you already have done enough research, or there is already enough research in the world to fix it, or we're still getting there?
Mm-hmm. Yeah. By the way, I think the rule path is not limited domain. They are pretty general because you can deploy in everybody's home. Everybody's home is different. And you have different objects, different environments. They're so different. It's definitely not limited, I would say. A limited domain is in a controlled environment in the lab, for example. You have very clean table, very good light, and they are all the same. That's limited domain, I would say. Yeah. In terms of my research, I think we are still not there yet. Even for one particular task, for example, cooking, it's still not solved because if you want to deploy into the real world, there are so many uncertainties and difference and personalization, a lot of things. I think currently, I think especially in humanoid and manipulation, I think they are far from solved. Speaking of any of the specific domain.
Okay, we will invite you next year and see how close you're getting to pet cat or pet dog. Okay, we received. Okay, Alex. Yeah.
No, if there's another one, go ahead.
Yeah. There is a comment, I believe. Thank you, great presentation and very interesting work. I really enjoyed seeing logics like temporal logic being integrated into the learning mechanism. This is just a comment, no question here. Another great presentation and questions. Okay, I think, one more questions. I was thinking your work can be applied to computer use itself. Isn't that a good limited domain? If you have access to it, a lot of things can be already be labeled.
I didn't really get this question. Computer usage?
Yes, I'm not sure I understand. It can be applied to computer use itself.
Maybe that means like operating a user interface. There's something called robotic process automation, which means they don't mean real robots. They mean like controlling the cursor, in a user interface, this kind of thing.
Yeah, if it mean the virtual assistant, I think it would definitely be useful. For example, for our web agents, like help us book flights, or you have the visual input that the human have, then you definitely can use this to make it more trustworthy and also generalizable. And the other thing I'm thinking of this is maybe we're talking about that like the human in the loop decision system. So for example, we want the human and the machine or the either agents or robot to make decision jointly. Then we could also create such an interface, allow them to communicate and collaborate when when making a final decision. For example, the robot could propose something and have its explanation is like rationale and whatever. Then the human can actually come in to see whether it want to intervene or approve or provide another reasoning, for example, them to make the final decision. And also in this process, the human can also provide, for example, some guidance, high-level guidance or knowledge to guide the robot reasoning or steer the reasoning, for example. I also have a recent work on multi-agent collaboration, but that's all on the agent side, like collaboration among the agents. So what we do is instead of letting the agents to communicate in natural language, we want them to have a thought communication. So we identify what are the key concepts. Then we ask them to communicate to each other using the thoughts directly, which is more efficient.
Mm-hmm. Thank you, Yaqi. A follow-up question, maybe from a different user, but still. Are there software implementations we can experiment with regarding these applications to computer usage, to a graphical user interface that you just mentioned?
Mm-hmm. Yeah, I am not very familiar with the web agents yet. I'm planning to do that. I think it's really useful. I think it really depends on different domains. For example, if you want to manage our email, there probably some constraint, like safety constraint, either safety constraints or common sense constraint. For example, how you address people and how you organize the email. And I think there's also some personalized needs. And what I think the advantage of my line of work is that it allow you to input your own preferences. Like if you want it to behave this way or that way, you can tell it use natural language. Then we can easily convert that natural language into our structural knowledge and use that structural knowledge to guide the behavior of the agents.
Mm-hmm. Thank you. And I think we're done with questions. Just a couple more comments that I would like to read. Self-driving cars also use remote assistance to compensate for lack of Kahneman's system 2. And thanks for the insightful presentation. See you next week.
Thank you.
Since we have a few minutes, I'll just ask one. I have many more questions, but I'll ask one technical question. So I hadn't seen D, DN, and F before, but that's intriguing. So is it the case that it gives, I think what you're saying is it gives a unique, well, are you saying that it gives a unique kind of representation for any particular logical expression? And therefore you can think of it as semantically unique, or given a semantics, it's unique. But if that's the case, then does it sort of compete in the same realm as like binary decision diagrams? What's the relation to BDDs and things related to BDDs, like probabilistic circuits and so on?
Yeah, I think they're definitely related. So the DDNF, what they do is, I think intuitively they are partitioning the solution space into parts. So the partition is done by the OR, and the factorization is done by the AND node. So this structure is actually the partitioning that they organize the solution space in such a way that make it a model counting or finding a solution satisfiability checkings that are really easy. Yeah, I think that's indeed that related to that. Yeah, but I haven't explored how to leverage those yet. Maybe that might be a future direction.
Okay. Yeah, I find that very interesting. Okay, we're out of time. Thanks, everyone. Yaqi, if you have time, you could jump on Discord. If there are any other questions. But we'll be putting out the info on Yaqi's work, so that on Discord, so people can follow up. In particular, you should hire Yaqi. She's on the job market, and we are working with Yaqi, so I give a thumbs up. So if anyone wants to follow up, please do. Thanks, Yaqi, and great stuff, and we'll probably see you soon. Thanks, everyone.
See you. Bye-bye.